Hi everyone, welcome back. In the previous video, we watched how Andrej shared a simple baseline model for generating characters. So this model was a standard classical machine learning model called the bigram. And this bigram model predicts what's the next character given the previous character that it has seen. So how it does that is it keeps track of a two-dimensional table where every single row corresponds to the logits for all other characters in the vocabulary given this given character that it has seen. So we saw how we encoded each of these characters into a single number. So in this case, these numbers refer to the rows indexes in these two-dimensional embeddings. And the values inside each of these rows corresponds to, for example, a given number, in this case, a logit at index 0. This indicates like the log probability of encountering this given character at index 0, ID 0. So ID 0 in this case, in our embedding vocabulary, index 0 refers to the new line character. So that's pretty much how it works. So we saw how Andrej came up with the code for how to do a forward. So it takes in two-dimensional tensor where the first dimension refers to the batch and the second dimension refers to the block size. And the second parameter to this method, forward, is an optional target. So if you pass in a target, in other words, like the expected characters that it should see, like it should generate, then we are able to calculate the loss. And the loss over here is a torch tensor, but it's really a scalar. So these are details, so like it's not too important. But over here in this video, we'll be continuing on in Andrej's tutorial and we'll be showing how we can train the bigram model. In the previous video, we saw that without training the model would just generate gibberish, and that is understandable. Like the model hasn't learned anything from the text, and we have not use a loss function to understand like how far are we from the expected output and how are we tweaking our parameters such that when we do a forward, we get the actual character that should come next. So let's get started.
Okay, let's now train the model. So first, what I'm going to do is I'm going to create a PyTorch optimization object. So here we are using the optimizer Adam W. Now, in the Make More series, we've only ever used stochastic gradient descent, the simplest possible optimizer, which you can get using the SGD instead. But I want to use Adam, which is a much more advanced and popular optimizer, and it works extremely well. For typical good setting for the learning rate is roughly 3e-4, but for very, very small networks, like is the case here, you can get away with much, much higher learning rates, 1e-3 or even higher probably. But let me create the optimizer object, which will basically take the gradients and update the parameters using the gradients. And then here, our batch size up above was only 4. So let me actually use something bigger, let's say 32. And then for some number of steps, we are sampling a new batch of data. We're evaluating the loss. We're zeroing out all the gradients from the previous step, getting the gradients for all the parameters, and then using those gradients to update our parameters. So typical training loop, as we saw in the main.
My bad, I didn't catch some details that Andrej mentioned here. But to our viewers that are curious, like Andrej mentioned the difference between the optimizer stochastic gradient descent, SGD, as well as the Adam optimizer. So for the stochastic gradient descent optimizer, it calculates the gradient for a given training example, and it uses that itself for moving in the direction such that we reduce our loss function. But for the Adam optimizer, it has something called like a momentum. So it calculates the current gradient, but the real gradient that it uses for that training step is really a weighted average of all the previous gradients it has seen thus far, along with what it has seen. So what I did was to just quickly do a quick questionnaire, like I asked ChatGPT. I mean, ChatGPT doesn't always get it right, but I personally like to use ChatGPT to answer some quick questions that I have. So I would take the answers with a pinch of salt, but in my experience, like this explanation makes sense and is pretty truthful. So to answer that question, like stochastic gradient descent uses only the loss for that given trading example that it sees. But for the Adam optimizer, in this case, like they have like a weighted average component. So you can see that. So this component over here, this M over here represents the moving average estimate for gradients and squared gradients. So M represents the gradients, the gradient component, and V represents the squared gradient component. You might be asking, why do we need a squared gradient component? For now, I will let's just take it as it is. We will see the explanation just in a bit. So over here, the salient point here is, as we mentioned, the difference between Adam optimizers and the standard optimizer is that the Adam optimizer has a weighted average component. So it's not going to use the gradient just from this example. It will also keep track of the gradients it has seen thus far. So you can think of this, so just to be clear, this component over here that I'm highlighting over here represents the gradient from the current training example. So beta 1 over here is a hyperparameter that you can set. And over here, beta 1 is typically set to 0.9 in PyTorch. So you can see that this gradient would have about 10% of component for this M over here, which is this moving average estimate. Yeah, and this one over here, like that, since beta 1 is 0.9, M represents the previous gradient before the previous weighted average for M. Before seeing this training example, this would be 0.9 multiplied by itself. So what this means is that it has a momentum term where it uses 90%, where the current term of M depends on like the previous term the previous magnitude that it has. So same for V, but V in this case is typically set to 0.999. So what this means is that the moving average estimates for the squared gradients has a higher component, or rather I like to call it momentum or inertia. So the current example will not affect the calculations of M and V too much. So it's like momentum in a sense, like the intuition behind it, I guess, is if you are to use the stochastic gradient descent, then you'll be moving in very erratic patterns, like a Brownian motion of sorts sometimes. But for the Adam optimizer, thanks to the momentum term that it has, it's the direction changes tend to be smoother, and it tends to move more smoothly towards the local or the global minimum in the loss function. So that's pretty much the idea. So I hope that was useful. And if you're curious exactly how M and V is used in optimizing our parameters, then yeah, this is pretty much the formula. So I will leave that to another video or another session, but that is pretty much the essence. In summary, you can think of the Adam optimizer as having a momentum term, and that's really an understatement. There's also other details such as Adam adjusting the learning rate adaptively for each parameter, while stochastic gradient descent uses a fixed learning rate. I mean, these are details, but you can think of the Adam optimizer as a more sophisticated but better optimizer over the stochastic gradient descent optimizer. So that's pretty much it.
The Make More series.
So
okay, let's now train the model. So first, what I'm going to do is
I missed out some details, so I'm just going to rewatch this snippet again.
I'm going to create a PyTorch optimization object. So here we are using the optimizer Adam W. Now, in the Make More series, we've only ever used stochastic gradient descent, the simplest possible optimizer, which you can get using the SGD instead. But I want to use Adam, which is a much more advanced and popular optimizer, and it works extremely well. For typical good setting for the learning rate is roughly 3e-4. But for very, very small networks, like is the case here, you can get away with much, much higher learning rates. 1 in -3, or even higher probably. But let me create the optimizer object, which will basically take the gradients and update the parameters using the gradients. And then here, our batch size up above was only 4. So let me actually use something bigger, let's say 32. And then for some number of steps, we are sampling a new batch of data. We're evaluating the loss. We're zeroing out all the gradients from the previous step, getting the gradients for all the parameters, and then using those gradients to update our parameters. So typical.
So to recap, we zero the gradients from the previous step over here by calling the zero gradient method on the optimizer. So one question that I have right now is like, what does this set to none do? So let's quickly take a look at this optimizer over here. So this is optimizer zero grad, so zero grad. Okay, let's take a look at this zero grad method over here. So it sets the gradient of all optimized torch tensors to 0. So okay, so we have an additional parameter here where we can either set the gradient to none or set to 0. But in this case, as you can see, like Andrej chose to set the gradients from the previous step to 0, sorry, to none instead of 0. So in general, like if we set this to none, this has lower memory footprint and can modestly improve performance, but it changes specific behaviors. So I guess Andrej chose to set this to none to save memory over here, but it changes certain behavior. So when the user tries to access a gradient and perform manual operations on it, a none attribute or tensors for 0 will behave differently. I guess that's true. I mean, if your gradients are zeros and nuns, it'll be different. If the user requests this, which we are, followed by a backpass, like we are doing a backpass after that. So gradients are guaranteed to be none for parameters that did not receive a gradient. So in this case, I don't think we have this situation, but the torch optim has different behavior if the gradient is 0 or none. In one case, it does a step with gradient 0, in another case, another one, it skips the step altogether. So in this case, like we do skip the gradient step since we are using this as none. In summary, I'm not too sure exactly why we would set to none to be true, but for now I would trust Andrej's judgment and just go ahead with this tutorial. So the second thing that we did is we called backward method on the torch tensor. So let's quickly take a look at torch tensor. Okay, torch tensor, and let's take a look at backwards. And if I'm mistaken, according to Andrej, like calling backward on the torch tensor calculates the gradient for the next step. So let's take a look. So torch tensor, let's take a look at backward. Okay, and here it is. Let's take a look. Gradient backwards, backward tensor, backward. There it is. So it computes the gradient of the current tensor with respect to the graph leaves. Not exactly sure what graph leaves mean, but the graph is differentiated using a chain rule. If the tensor is non-scalar and requires a gradient, in this case our tensor is a scalar, so this doesn't apply, and requires a gradient, the function additionally requires specifying gradient. So we didn't have to do that because our loss is a single scalar, and it should be a tensor of matching type and location that contains the gradient of the differentiated function with respect to self. Okay, I don't think I fully understand this thing here. Okay, but okay. I don't think that's very important anyway. So the function accumulates gradients in the leaf. You might use 0 gradient attributes to set them to none before calling it. Okay, so that's why. So according to the documentation, before calling backwards, we should 0 the gradient attributes or set them to none. So I'm not sure what leaves mean though. I think I'm missing some prerequisites here, but specifically what are graph leaves in Torch? But I think it's okay. I think we can just, I mean, even though our current understanding is rather sparse, I know enough that this backward method computes the gradient of the current tensor, or rather the current loss over here. So okay, it's calculating the gradient of the loss function. That's pretty much it. And optimizer step. Let's take a look at AdamW optimizer step. Step. Perform a single optimization step. So it takes in a closure, and I don't think we are using a closure over here. Yeah, it looks like we don't. So we are pretty much performing an optimization with respect to the gradients that we calculated. Yeah, that's pretty much it. So we are minimizing our loss and moving in the direction, and we are changing our parameters in the direction such that we reduce the loss. So that's pretty much it.
Typical training loop, as we saw in the Make More series. So let me now run this for, say, 100 iterations, and let's see what kind of losses we're going to get. So we started around 4.7, and now we're getting down to like 4.6, 4.5, etc. So the optimization is definitely happening, but let's sort of try to increase the number of iterations and only print at the end, because we probably want to train for longer. Okay, so we're down to 3.6 roughly. Roughly down to 3. This is the most janky optimization. Okay, it's working. Let's just do 10,000.
Let's try this ourselves as well. So let's use this, and here we are. So let's set this to a higher number. Let's try 10,000, and let's see if we are able to optimize it well. So now we are running the training loop. 5 seconds, 6 seconds. Okay, and we get 2.3. Yeah, I'm pretty sure like one common question is what's a good loss that we are going for. In my experience, the rule of thumb is if we continue to train and we notice that the loss function doesn't budge anymore, then, or rather doesn't budge much, then I guess that's a pretty decent gauge of when to stop. So you can set like a threshold for how much you expect the loss to change, and if the change in the loss is lesser than this threshold, then you can stop it. So you can see like we ran this 3 times, like 30,000 iterations, and the loss is still at 2.5. So I guess my assumption is that Andrej will probably stop around 2.5 as well.
And then from here, we want to copy this. And hopefully, we're going to get something reasonable. And of course, it's not going to be Shakespeare from a bigram model, but at least we see that the loss is improving. And hopefully, we're expecting something a bit more reasonable. Okay, so we're down at about 2.5-ish. Let's see what we get. Okay, well, dramatic improvement certainly on what we had here. So let me just increase the number of tokens. Okay, so we see that we're starting to get something at least like reasonable-ish. Certainly not Shakespeare, but the model is making progress. So that is the simplest possible model. So now what I'd like to do is, obviously this is a very simple model because the tokens are not talking to each other. So given the previous context of whatever was generated, we're only looking at the very last character to make the predictions about what comes next. So now these tokens have to start talking to each other and figuring out what is in the context so that they can make better predictions for what comes next. And this is how we're going to kick off the transformer. Okay, so next, I took the code that we developed in this Jupyter notebook and I converted it to be a script. And I'm doing this because I just want to simplify our intermediate work into just the final product that we have at this point. So in the top here, I put all the hyperparameters that we've defined. I introduced a few, and I'm going to speak to that in a little bit. Otherwise, a lot of this should be recognizable. Reproducibility, read data, get the encoder and the decoder, create the train and test splits, use the kind of like data loader that gets a batch of the inputs and targets. This is new, and I'll talk about it in a second. Now this is the bigram language model that we developed, and it can forward and give us a logits and loss, and it can generate. And then here we are creating the optimizer, and this is the training loop. So everything here should look pretty familiar. Now, some of the small things that I added. Number one, I added the ability to run on a GPU if you have it. So if you have a GPU, then this will use CUDA instead of just CPU, and everything will be a lot more faster. Now, when device becomes CUDA, then we need to make sure that when we load the data, we move it to device. When we create the model, we want to move the model parameters to device. So as an example, here we have the NN embedding table, and it's got a .weight inside it, which stores the sort of lookup table. So that would be moved to the GPU, so that all the calculations here happen on the GPU, and they can be a lot faster. And then finally here, when I'm creating the context that feeds it to generate, I have to make sure that I create on the device. Number two, what I introduced is the fact that here in the training loop, here I was just printing the loss.item inside the training loop. But this is a very noisy measurement of the current loss because every batch will be more or less lucky. And so what I want to do usually is I have an estimate loss function, and the estimate loss basically then goes up here, and it averages up the loss over multiple batches. So in particular, we're going to iterate eval iter times, and we're going to basically get our loss, and then we're going to get the average loss for both splits. And so this will be a lot less noisy. So here, when we call the estimate loss, we're going to report the pretty accurate train and validation loss. Now, when we come back up, you'll notice a few things here. I'm setting the model to evaluation phase, and down here, I'm resetting it back to training phase. Now, right now for our model as is, this doesn't actually do anything, because the only thing inside this model is this nn.embedding, and this network would behave the same in both evaluation mode and training mode. We have no dropout layers, we have no batch drum layers, etc. But it is a good practice to think through what mode your neural network is in, because some layers will have different behavior at inference time or training time. And
yeah, some layers that Andre might probably mention later is, for example, dropout. So during training time, some of the connections between layers would automatically be dropped so that we regularize the model, in a sense that we force the model to not depend too much on specific on some specific parameters inside the model. So on top of that, there's others as well. If I'm not mistaken, batch normalization as well. And batch normalization is only enabled in training and not during evaluation. So it makes sense that in Andre's function over here, estimate loss, he changed the models to evaluation mode before we calculate the estimate loss over here and set it back to train if we happen to train. I think which we are calling this method during training. So it makes sense that he would call .train on this model. It's pretty decent, I guess, for this implementation is pretty decent for this prototype over here. Second thing I'm kind of curious is like, or rather I'm not sure, is like, what is this function wrapper by Torch? Torch.nograd. Let's quickly do a quick search. Torch.nograd. Okay, there we are. So it's a context manager that disables gradients calculations. And it's useful for inference when you are sure you will not call Torch backwards. It will reduce memory consumption for computation that would otherwise require gradients equals to true. And in this mode, the result of every computation will have requires grad equals to false, even when inputs have requires gradient. Okay. So I guess if you wrap a function under torch.nograd, then we disable gradient calculations. Makes sense. Makes sense. Anything that is not related to any function that doesn't require gradient calculations should be wrapped by this function signature, I guess, by this function wrapper. So okay, I guess this makes sense.
There's also this context manager, torch.nograd, and this is just telling PyTorch that everything that happens inside this function, we will not call .backward on. And so PyTorch can be a lot more efficient with its memory use because it doesn't have to store all the intermediate variables because we're never going to call backward. And so it can be a lot more memory efficient in that way. So also a good practice to tell PyTorch when we don't intend to do backpropagation. So right now, this script is about 120 lines of code and that's kind of our starter code. I'm calling it bygram.py and I'm going to release it later. Now running this script gives us output in the terminal and it looks something like this. It basically, as I ran this code, it was giving me the train loss and val loss, and we see that we convert to somewhere around 2.5 with the bygram model. And then here's the sample that we produced at the end. And so we have everything packaged up in the script, and we're in a good position now to iterate on this. Okay, so we are almost ready to start.
Let's do our homework and let's see if we can find that Python script that Andrej created for us. Let's take a look at his repository, and oh nice, he has the bygram file over here. So he does have a readme and everything here. Oh, that's really so nice of Andrej. So let's copy this and let's try running it ourselves. So let's copy this. I mean, I could clone it, but it would be nice if I could create it from scratch. So let's remove this and use this instead. Let's rename this to bygram. And of course, we will need some dependencies. Let's install the requirements. So torch, I'm pretty sure he has a requirements. Oh, he does have requirements.txt file here. Interesting. But I think we already installed torch here. So we're using 1.13.1, and we are also using, oh, that's all? That's all dependencies? Okay, init, status, okay, nice. And let's take a look. So we have a batch size, we have a log size. Yeah, let's quickly add in mypy as well. Let's use mypy for type checks. So mypy documentation. Yeah, let's just include mypy as well. mypy 0.991 install mypy equals to 0.991. So we got it. Now let's get started. mypy ini. Is there an ini? Configuration file. Yes, I'm looking for the configuration file that would make the mypy check more convenient. Okay, mypy configuration file. There we are. Okay. Nice. So let's use this. And this is a simple customization to our mypy check. So let's create mypy ini file here. We'll use this for type checking, and we can do the mypy run. Okay, so looks like we need to set a package, a mypy path, I guess. So let's do is it mypy path, I guess? String. Okay, there's something like this equals to this file, this document, this target here. No, okay, interesting. Okay, it's okay. I guess we will stick to this for now and just mypy run dot bigram.py. So we are running this command here to type check bigram for now, and there's no errors for now, so that's nice. So let's try running bigram.py, and this should, oh yes, of course we need the input file as well, so let's get that. Okay, view file, yeah, let's just, okay, I guess I can copy it, input.text, nice. Now let's try running the bigram model again, and let's see if we can get it training. Nice, it works. Okay, and as we can see, like just like what Andrej mentioned, like it's getting somewhere, but it's not perfect. And understandably, this doesn't work too well because how we generate a given character or word is going to depend more than just the previous character that we see before. So maybe there's some missing information that we're not giving to the model. Specifically, we are not letting a given token or character in this case like pay attention to other tokens in before that comes before. So maybe 10 characters down, maybe 20, 30, 40 characters down matters aside from just one character back. So okay, anyway, we managed to get it running, so let's continue with watching the lecture.
Writing our very first self-attention block for processing these tokens. Now, before we actually get there, I want to get you used to a mathematical trick that is used in the self-attention inside a transformer, and is really just like at the heart of an efficient implementation of self-attention. And so I want to work with this toy example to just get you used to this operation, and then it's going to make it much more clear once we actually get to it in the script again. So let's create a b by t by c, where b, t, and c are just 4, 8, and 2 in this toy example. And these are basically channels, and we have batches, and we have the time component, and we have some information at each point in the sequence, so c. Now, what we would like to do is we would like these tokens, so we have up to 8 tokens here in a batch, and these 8 tokens are currently not talking to each other, and we would like them to talk to each other. We'd like to couple them. And in particular, we want to couple them in a very specific way. So the token, for example, at the 5th location, it should not communicate with tokens in the 6th, 7th, and 8th location, because those are future tokens in the sequence. The token on the 5th location should only talk to the one in the 4th, 3rd, 2nd, and 1st. So information only flows from previous context to the current time step. And we cannot get any information from the future because we are about to try to predict the future. So what is the easiest way for tokens to communicate? Okay, the easiest way I would say is, okay, if we're a 5th token and I'd like to communicate with my past, the simplest way we can do that is to just do an average of all the preceding elements. So for example, if I'm the 5th token, I would like to take the channels that make up that are information at my step, but then also the channels from the 4th step, 3rd step, 2nd step, and the 1st step. I'd like to average those up, and then that would become sort of like a feature vector that summarizes me in the context of my history. Now, of course, just doing a sum or like an average is an extremely weak form of interaction. Like, this communication is extremely lossy. We've lost a ton of information about the spatial arrangements of all those tokens, but that's okay for now. We'll see how we can bring that information back later. For now, what we would like to do is, for every single batch element independently, for every teeth token in that sequence, we'd like to now calculate the average of all the vectors in all the previous tokens and also at this token. So let's write that out. I have a small snippet here, and instead of just fumbling around, let me just copy paste it and talk to it. So in other words, we're going to create X, and BOW is short for bag of words, because bag of words is kind of like a term that people use when you are just averaging up things. So this is just a bag of words. Basically, there's a word stored on every one of these 8 locations, and we're doing a bag of words, so just averaging. So in the beginning, we're going to say that it's just initialized at 0, and then I'm doing a for loop here, so we're not being efficient yet. That's coming. But for now, we're just iterating over all the batch dimensions independently, iterating over time, and then the previous tokens are at this batch dimension, and then everything up to and including the teeth token. Okay? So when we slice out x in this way, xprev becomes of shape how many t elements there were in the past, and then of course c, so all the 2-dimensional information from these little tokens. So that's the previous sort of chunk of tokens from my current sequence. And then I'm just doing the average, or the mean, over the 0th dimension. So I'm averaging out the time here. And I'm just going to get a little c 1-dimensional vector, which I'm going to store in x bag of words. So I can run this, and this is not going to be very informative because, let's see, so this is x of 0, so this is the 0th batch element, and then expo at 0. Now, you see how at the first location here, you see that the 2 are equal, and that's because it's we're just doing an average of this 1 token. But here, this one is now an average of these 2. And now this one is an average of these 3, and so on. So, and this last one is the average of all of these elements. So vertical average, just averaging up all the tokens, now gives this outcome here. So this is all well and good, but this is very inefficient. Now the trick is that we can be very, very efficient about doing this using matrix multiplication.
Okay, just before Andrej moves on to the alternative for bag of words, let's quickly break down one little prerequisite here. So torch.ren_n seems pretty similar to NumPy's ren_n, but just to be sure, let's take a look at what exactly it does. So it returns a tensor filled with random numbers from a normal distribution with mean 0 and variance 1. I see, okay. And in this case, we passed in 3 inputs, so B, T, and C. So B, T, and C, I guess that's the size. So if you pass in three dimensions, then it will give you a torch tensor with exactly that dimension, but the numbers would be from 0 with a variance of 1. So okay, that makes sense. Okay, that makes sense.
So that's the mathematical trick. And let me show you what I mean. Let's work with the toy example here. Let me run it and I'll explain. I have a simple matrix here that is a 3 by 3 of all ones, a matrix B of just random numbers, and it's a 3 by 2, and a matrix C, which will be 3 by 3 multiplied 3 by 2, which will give out a 3 by 2. So here we're just using matrix multiplication. So A multiplied B gives us C. Okay, so how are these numbers in C achieved, right? So this number in the top left is the first row of A dot product with the first column of B. And since all the row of A right now is all just ones, then the dot product here with this column of B is just going to do a sum of this column. So 2 plus 6 plus 6 is 14. The element here in the output of C is also the first column here, the first row of A, multiplied now with the second column of B. So 7 plus 4 plus 5 is 16. Now you see that there's repeating elements here. So this 14 again is because this row is again all ones, and it's multiplying the first column of B. So we get 14. And this one is, and so on. So this last number here is the last row, dot product, last column. Now the trick here is the following. This is just a boring number of, it's just a boring array of all ones, but Torch has this function called trill, which is short for a triangular, something like that. And you can wrap it in torch.once, and it will just return the lower triangular portion of this. Okay. So now it will basically zero out these guys here. So we just get the lower triangular part. Well, what happens if we do that? So now we'll have A like this and B like this. And now what are we getting here in C? Well, what is this number? Well, this is the first row times the first column. And because this is zeros, these elements here are now ignored. So we just get a 2. And then this number here is the first row times the second column. And because these are zeros, they get ignored, and it's just 7. This 7 multiplies this 1. But look what happened here. Because this is 1 and then zeros, what ended up happening is we're just plucking out this row of B, and that's what we got. Now here, we have 1, 1, 0. So here, 1, 1, 0 dot product with these two columns will now give us 2 plus 6, which is 8, and 7 plus 4, which is 11. And because this is 1, 1, 1, we ended up with the addition of all of them. And so basically, depending on how many 1s and 0s we have here, we are basically doing a sum currently of a variable number of these rows, and that gets deposited into C. So currently we're doing sums because these are 1s, but we can also do average, right? And you can start to see how we could do average of the rows of B sort of in an incremental fashion. Because we can basically normalize these rows so that they sum to 1, and then we're going to get an average. So if we took A, and then we did A equals A divide, torch.sum in the of A in the 1th dimension, and then let's keep them as true. So therefore the broadcasting will work out. So if I rerun this, you see now that these rows now sum to 1. So this row is 1, this row is 0.5, 0.5 is 0, and here we get 1/3. And now when we do A multiply B, what are we getting? Here we are just getting the first row. Here now we are getting the average of the first two rows. Okay, so 2 and 6 average is 4, and 4 and 7 average is 5.5. And on the bottom,
That was pretty surprising. I wasn't expecting this hack here, where we can use this trill method on this trill function on Torch to come up with a triangular matrix, and this triangular matrix does a good job of like so-called masking over the tensors in B. So wow, that's so mind-blowing.
on the bottom here, we're now getting the average of these three rows. So the average of all of elements of B are now deposited here. And so you can see that by manipulating these elements of this multiplying matrix, and then multiplying it with any given matrix, we can do these averages in this incremental fashion, because we just get, and we can manipulate that based on the elements of A. Okay, so that's very convenient. So let's swing back up here and see how we can vectorize this and make it much more efficient using what we've learned. So in particular, we are going to produce an array A, but here I'm going to call it way, short for weights. But this is our A. And this is how much of every row we want to average up. And it's going to be an average because you can see that these rows sum to 1. So this is our A. And then our B in this example, of course, is X. So what's going to happen here now is that we are going to have an expo 2. And this expo 2 is going to be way multiplying Rx. So let's think this through. Way is T by T. And this is matrix multiplying in PyTorch a B by T by C. And it's giving us what shape? So PyTorch will come here and it will see that these shapes are not the same. So it will create a batch dimension here. And this is a batched matrix multiply. And so it will apply this matrix multiplication in all the batch elements in parallel and individually. And then for each batch element, there will be a T by T multiplying T by C exactly as we had below. So this will now create B by T by C, and expo 2 will now become identical to expo. So we can see that torch.allClose of expo and expo 2 should be true. Now, so this kind of like convinces us that these are in fact.
Wow, I didn't know about this broadcasting as well. Like, I didn't know that you could matrix multiply TT with BTC, and Torch would be so smart to infer that it should broadcast along the batch dimension. Wow, that's so good. And the second thing that I find it quite curious is all close over here. Okay, so before I digress, way.sum1, this sums up all the numbers in the horizontal axis. So if we want it to sum up vertically axis, we will pass in 0 for the first parameter. But for all close over here, let's quickly go and search what exactly does it does. My assumption is that that's a method that checks if two tensors have all of their elements close to each other. So torch.allClose. Okay, so there is a threshold, I guess. Yeah, and yeah, like its name suggests, I guess, like it's checking whether if the two vectors are really close to each other.
Act the same. So xbow and xbow2, if I just print them, okay, we're not going to be able to okay, we're not going to be able to just stare it down, but well, let me try xbow basically just at the 0th element and xbow2 at the 0th element. So just the first batch, and we should see that this and that should be identical, which they are. Right? So what happened here? The trick is we were able to use batched matrix multiply to do this aggregation, really. And it's a weighted aggregation, and the weights are specified in this t by t array. And we're basically doing weighted sums. And these weighted sums are according to the weights inside here, they take on sort of this triangular form. And so that means that a token at the tth dimension will only get information from the tokens preceding it. So that's exactly what we want. And finally, I would like to rewrite it in one more way, and we're going to see why that's useful. So this is the third version, and it's also identical to the first and second. But let me talk through it. It uses softmax. So trill here is this matrix, lower triangular ones. Way begins as all 0. Okay, so if I just print way in the beginning, it's all 0. Then I used masked fill. So what this is doing is way.masked fill, it's all zeros, and I'm saying for all the elements where trill is equals 0, make them be negative infinity. So all the elements where trill is 0 will become negative infinity now. So this is what we get. And then the final line here is softmax. So if I take a softmax along every single, so dim is -1, so along every single row, if I do a softmax, what is that going to do? Well, softmax is also like a normalization operation, right? And so spoiler alert, you get the exact same matrix. Let me bring back the softmax. And recall that in softmax, we're going to exponentiate every single one of these, and then we're going to divide by the sum. And so if we exponentiate every single element here, we're going to get a 1, and here we're going to get basically 0, 0, 0, 0, 0 everywhere else. And then when we normalize, we just get 1. Here we're going to get 1, 1, and then zeros, and then softmax will again divide, and this will give us 0.5, 0.5, and so on. And so this is also the same way to produce this mask. Now, the reason that this is a bit more interesting, and the reason we're going to end up using it in self-attention, is that these weights here begin with 0. And you can think of this as like an interaction strength, or like an affinity. So basically, it's telling us how much of each token from the past do we want to aggregate and average up. And then this line is saying tokens from the past cannot communicate. By setting them to negative infinity, we're saying that we will not aggregate anything from those tokens. And so basically, this then goes through softmax and through the weighted, and this is the aggregation through matrix multiplication. And so what this is now is, you can think of these as, these zeros are currently just set by us to be 0, but a quick preview is that these affinities between the tokens are not going to be just constant at 0, they're going to be data dependent. These tokens are going to start looking at each other, and some tokens will find other tokens more or less interesting. And depending on what their values are, they're going to find each other interesting to different amounts, and I'm going to call those affinities, I think. And then here we are saying the future cannot communicate with the past. We're going to clamp them. And then when we normalize and sum, we're going to aggregate sort of their values depending on how interesting they find each other. And so that's the preview for self-attention. And basically, long story short from this entire section is that you can do weighted aggregations of your past elements by using matrix multiplication of a lower triangular fashion. And then the elements here in the lower triangular part are telling you how much of each element fuses into this position. So we're going to use this trick now to develop the self-attention block. So first, let's get some quick preliminaries out of the way.
Nice. So at this point, we covered quite a lot thus far. We have covered from training the bigram model all the way until we reached just before the start of minor code cleanup. This video was really, like, it has surprised me on many levels. Like, I loved how Andrej went through the chain of thought in a very intuitive way. Like, we trained the bigram model. I mean, plotting a script there wasn't much information there, but he also talked about how we can aggregate information of what characters have appeared in the past by doing an average of that. And that itself is a trivial intuition, but I loved how Andrej took it a step further and iteratively show us how we can implement it using for loops. He went on to come up with the matrix multiplication strategy where he used the trill method to come up with the triangle, make every single one of these rows, divide each of these ones in each of these rows such that all the numbers in the row add up to 1, and that gives us the average, so-called an average weight of every single token before a given token. And wow, we could actually use matrix multiplication to matrix multiply that trill vector with x, and all of a sudden, like, we have this mask attention right now where every single token, when we're deciding to generate a given token, it can only pay attention to the information of all tokens that come before it and not after it. He went on to talk about how we can implement it in a more intuitive way using mask fill. And I personally agree that using mask fill is more intuitive than the second method, even because the second method requires you to divide the numbers in the trill by the sum along the horizontal axis. I mean, wow, that's not very readable. But the mask fill strategy is intuitive. The softmax strategy, the mask fill and softmax strategy is much more readable. So this is, wow, I'm really impressed by Andrej. Like, this, it has been a great experience thus far, and wow, like, I have learned a lot in the details of the implementation. So that's it for this video. That's it for this third part of our looking at Andrej implement this baselines and stuff. And looks like we have a lot of interesting things coming up. Looks like Andrej will be talking about positional encodings later on. So I'm really excited thus far. I really love this, and yeah, I would have done it all over again and watched Andrej build this from scratch. So Andrej, if you're watching this, thank you so much. I found this very helpful. And yes, that's it for this video, and we'll see you in the next one.